Human mathematics is continuous. We count in tens because of our biology, naturally perceiving the world in fluid, unbroken gradients. But digital computing environments cannot rely on continuous values. Inside a processor, information snaps into distinct, discrete states. This restriction is dictated by the physical behavior of semiconductive switches. Electricity is either permitted to flow or it is blocked. Voltage is either high or low, on or off. The base 2 binary system is the only mathematically rigorous way to map logic directly to this physical current. Binary is structurally perfect for driving silicon gates, but for human engineers attempting to interface with that hardware, base 2 creates an immediate bottleneck. The resulting strings of ones and zeros are so dense and verbose that reading them, transcribing them, or using them for memory management introduces severe practical challenges. To bypass this bottleneck, digital architecture relies on a mathematical abstraction layer, base 16, or hexadecimal. Hexadecimal functions as a high-density compression system, mathematically anchored to the processor's physical limits through its power of 2 relationship with binary. Scaling a system to address millions of bytes without its structural logic collapsing requires understanding this specific stack. We have to trace the architecture from the raw voltage of physical gates up through binary arithmetic and finally into the hexadecimal memory models that make modern software possible. Every numeral system utilized in computing relies on the axiom of positional weight. The mathematical value of any given digit is strictly defined by its base, raised to the power of its position index. This cascading diagram illustrates the successive division algorithm used to translate decimal integers into processor-ready formats. We repeatedly divide the decimal value by the target base, either 2 or 16, and extract the new positional digits by logging the remainders until the quotient hits 0. Reversing this process requires weighted summation. We map the binary or hex sequence back to decimal by expanding it into its power series, multiplying each digit by its positional weight and adding the results. This 16-bit binary sequence reveals the structural efficiency of base 16. Because 2 to the 4th power is 16, we perfectly slice any binary string into distinct 4-bit blocks called a nibble. Every mathematical variation of a nibble collapses perfectly into a single hexadecimal character. 1010 maps exactly to A and 1111 to F. This exact 4-to-1 direct mapping compresses data density. It gives programmers the ability to write dense memory addresses concisely, without discarding the underlying bit-level logic required by the actual transistor gates. Translating the data is only the first requirement. The Arithmetic Logic Unit inside a microprocessor must physically execute calculations using those binary voltage states. Binary arithmetic follows rigid positional rules. The system relies on 4 basic states of addition, with the most critical occurring when adding 1 and 1. Because the current column reaches its limit, the sum is 0, and the system is forced to carry a 1 to the next positional index. Hardware architects instantiate these mathematical carrying rules physically using logic gates. Specifically, they arrange NOT, AND, OR, and XOR gates to permit or prevent electrical current based on their combination of inputs. This half-adder calculates the sum and carry of 2 bits. Lacking a carry-in, a third input creates a full adder. These cascade into a ripple carry adder, where the carry ripples sequentially to the next most significant bit. That sequential ripple creates a physical delay. Waiting for a carry to traverse every bit severely throttles performance. To execute math at modern clock speeds, engineers implement carry look-ahead logic, adding predictive circuits that determine carry propagation in advance to bypass the bottleneck. Processing addition requires massive gate arrays, yet digital hardware rarely includes dedicated subtraction circuits. Building physical subtractors consumes extremely valuable silicon space. 2's complement manages negative numbers without a physical minus sign. It first finds the 1's complement by toggling all bits. Then, adding a 1 to the least significant bit ripples across, forcing the far left bit to designate the sign. 2's complement solves 2 critical engineering problems. It establishes a single, unique binary sequence for 0, simplifying the logic. And it allows the ALU to execute subtraction using its standard addition hardware, simply by adding the 2's complement of the subtrahend. The trade-off for this arithmetic efficiency is an asymmetrical number range. An 8-bit system shifts from balanced to representing -128 through +127. Computer subtraction is an engineered illusion constructed entirely from addition logic. While the ALU arithmetic is efficient, routing data through complex addition cycles is often too slow for the demands of performance-heavy embedded systems. This register shows how developers bypass the ALU by interacting directly with the hardware using bit shifting. Physically sliding the binary sequence left multiplies the exact value by 2, while shifting right instantly divides the value by 2. Developers simultaneously rely on bit masking to isolate and manipulate specific individual bits without overwriting the surrounding data. A bitwise OR operation forces specific bits to a true or on state. A bitwise AND combined with a negated mask clears bits, forcing them off, and a bitwise XOR operation toggles bits perfectly from their existing state. Bypassing the clock cycles required for standard ALU multiplication through immediate bitwise shifts and logical toggles provides a significant speed advantage. Operating data as a direct map of physical toggle switches yields the extreme throughput required for performance-heavy tasks like high-speed cryptography and real-time graphical rendering. As we pull back from processor arithmetic to examine system-level memory management, hexadecimal notation becomes the mandatory standard for organizing large datasets. This equation illustrates the segmented addressing model designed for the Intel 8086. Early 16-bit processors had to address a full megabyte of memory using registers that were far too narrow. To solve this, a 16-bit segment address shifts left by 4 bits, mathematically multiplying its value by 16. A secondary 16-bit offset drops in and adds directly to that shifted segment. This compound logic cleanly outputs a 20-bit physical address. Modern network architecture requires drastically wider addressing spaces. The IPv6 standard relies on 128 bits. Since parsing a string of 128 individual binary states is functionally impossible for human engineers, base 16 hextets become an absolute necessity for global routing infrastructure. Calculating these addresses is straightforward, but the physical rule governing how a system stores that large hex string in memory is dictated by endianness. This split layout maps how byte order diverges based on architecture. Network protocols are standardized on Big-Endian, storing the most significant byte at the lowest memory address. Conversely, standard x86 and ARM computer architectures prioritize Little-Endian logic, storing the least significant byte first to accelerate low-level processing. Binary states represent the physical reality of the silicon. Hexadecimal notation and bitwise math provide the architecture required to organize those states into modern digital logic.